Right. Right, thank you, and good afternoon, ladies and gentlemen. I'm going to talk unashamedly from a personal standpoint today. And before I do that, I'm going to put this on. It's not just in case you throw anything at me. Some of you might feel like doing so by the end, but to remind you that I come to this with wearing a completely different hat from what everybody else does in this room. I'm an engineer. I'm not a scientist or a mathematician, and an engineer's viewpoint is a different one. So just remember, when you want to throw something at me, I've got my hat on. So.
We have shoes.
And I can duck just as well as George Bush. Right. Contents of my presentation. First of all, I'll talk a little bit about why we want to model, what the engineer's perspective is on that, some real system problems in, I'm thinking here, industrial powder processing, which is what I'm talking about, some experience we have with modeling different states, some challenges, and a special offer at the end. So, what does humanity need models for? Maybe all sorts of reasons why we might want models. Is it an idyll for which to strive? Is it maybe a representation of reality as we would like it to be, or maybe just as we can understand it? So, the engineer's privilege, of course, is to make things. And we want to make things that are safe, things that are affordable, and things that work as we want them to work. The other side of that is if our designs don't work, we're likely to lose our reputation and with it our livelihood. And if people have paid money and built things that don't work to our designs, we may be sued. And if those things fall on people's heads, we may go to prison. So we have a particular perspective on models. Right. Engineers need models so that we can predict how a system will work when we are going to build it. Its function, its lifetime, its stability, but also to answer those what-if questions. You know, what if I change this size pipe for that size pipe? What if I make the hopper angle this instead of this? We need models to answer those kind of questions. We need our models to be adequately accurate, not necessarily absolutely, but to get us to what is the right solution. We need them to be accessible. We need to be able to use them cheaply as well, without special mathematical expertise or great expense. Engineers are not frightened of a bit of mathematics, you know. We can cope with a few differential equations, but once we start to see curly D's, we start to break out in a sweat. We need our models to be reliable for obvious reasons, and we also want our models to be validated to give us some confidence. Generally, our order of preference in using models, analytical models based on schoolroom physics is ideal. You know, we can understand those, we can use them, we're confident about them. Can't solve many problems with those, though, unfortunately. So in many cases, we use an analytical model that has perhaps, it's based on a simplified physical model, and then we empirically calibrate it. An awful lot of engineering is based on this approach. You know, the Fanning or Darcy expression from friction factors from the Moody diagram. And if we have to do it, we'll do material characterization tests to get those calibrations. If we can't do that, then we may be stuck with, as we are in many situations, empirical models for scale-up. We do a small-scale experiment, and then we have some sort of scaling rules to predict what's going to happen in the real system. And numerical models, by and large, are a last resort to us because of the cost and the time scale involved in them. And we'll only use them if there's nothing else, or if they give us a significant advantage to be able to do something we can't do any other way, such as finite element modeling, for instance, which is widely accepted now. Just turning back to what one or two other speakers have mentioned, how well do solids processing plants work? A report done a few years ago showed that 60% of solids handling systems, solids processing systems, never achieve the throughput and the performance that they're supposed to. And if you look at the technical risk and the cost overruns, the average cost overrun is over 100%. So these systems cost to get up and running more than twice the estimate on which the business case for investment was made. Now that's a pretty bad track record, I think you'll agree. And to be fair, quite a lot of that is because many people in the industry don't use the available models that there are. But it's also partly because our models aren't fully adequate in many instances. And the kind of things we finish up with are structural failures on silos, failures to discharge, the inevitable outbreak of hammer rash, as it's popularly known, on hoppers and silos. This was taken on a pharmaceutical plant, and this piece of stainless steel pipe here, actually, just out of shot, there's a number written on it. It's entered in the plant inventory log as the official piece of stainless steel pipe with which to beat the hopper. Material going through there is worth more than £1,000 a kilo. That was on the same plant. It was supposed to be a 24-hour-a-day plant, but they couldn't work through the night because the noise of people hammering silos kept residents awake on the adjacent housing estate. And of course, people, apart from hammering, they use aeration and all sorts of other things. On this hopper, they've even put valves up on the top, so when they get a blockage, they can get somebody round with an air lance to give the hopper an enema, you know, to get it moving. There's an example. One baghouse on a small power station. Cleaning costs them £88,000 a year in downtime. Segregation, another common problem. You put material in a hopper, when you discharge it, it comes out no longer mixed. Caking, material going hard. So that's just a few basic problems, by no means a thorough tour, but just a few illustrations. Just a little bit about the Wolfson Centre, so you get an idea of where we're coming from. The key point here is that within my team we occupy a fairly privileged position, in as much as that if you divide up our man hours, we spend about 50% of our time on research and most of the rest on advanced professional practice. So we get a lot of time to use the models that we're developing and also to use models from other people as well. So, as I say, that's quite a privileged position which we appreciate. Now, a few industrial applications of dense granular flow. Particle processing for extraction, manufacturing, all the rest of it, so storage, conveying, processing, mixing, size change, all of these kind of things. And a lot of people have talked about the importance of bulk solids or particulates or granular materials, and the name tends to depend upon what discipline you're working in, but the implication is the same. If you go around a supermarket, typically 20,000 lines in a supermarket, over 10% of those about 10% of those are actually bulk solids, and most of the rest depend on bulk solids one way or another. And of course, other bulk solids that are familiar to us. I don't want to exclude these from the scene, but nevertheless, what I'm focusing on is more the industrial minerals, industrial processing and such like. So I'm going to do a quick tour of some techniques that we've had experience with using for predicting dense and intermediate granular flows, which, although this conference is supposedly about dense granular flow, we've actually talked much more, I think, about the intermediate. And in many ways, that's where there's more challenges. Now, I'm going to talk about a lot of different techniques. Because of time, I'm not able to reference or credit all these different techniques. Some of these techniques are what we've developed in our group, some we've developed in collaboration with other groups, some we've just sort of brought in from others as well. But if anybody wants references, I can give you piles of them. So, models for dense conditions, where obviously, as we've heard, momentum effect is negligible. In most cases, in industrial applications, we're talking here of cohesive powders. Non-cohesive powders in the dense condition, industrially, is mostly a trivial case. In other conditions, not so, but in the dense condition. So it's non-fluidized cohesive powders. And it's a statics-driven problem. Failure occurs along planes where applied stress exceeds static strength. Crack propagation, repeated catastrophic failure of a loaded structure, if you like. The stresses redistribute, failure occurs along new planes. Self-localization of shear, as we've heard a lot about, is a big part of this. And that's one of the reasons why that happens. It's not the only reason, but it's a big contributor towards it. And of course, this is a two-stage process. A structure, a cohesive structure, is created by material being put, say, into a hopper. And then when you open the valve at the bottom, you hopefully get failure because of the change in load conditions. So we need to always be aware that flow of cohesive powders in the dense state is a two-stage process. Self-localization of shear, you see this everywhere where you see the flow of cohesive materials like this. So, techniques to solve these dense, slow flow problems. If you can describe the geometry mathematically, such as flow patterns in hoppers, stability embankments, a number of these other things, then you can do very well with analytical models based on statics. And one of the advantages of these analytical models is that you can feed in, as we've heard in terms of people talking about models for plasticity and all these kind of things, you can feed in some fairly complex constitutive models. You can account for cohesion, friction, volume change, and all of these other kind of things. But of course, you have to characterize the powder. So you've got to get that constitutive behavior. And again, that is a two-stage process. You've got to consolidate the powder, then fail it. And that's what we do with shear cells. So you predict the consolidating load in the system. You predict the strength that that lends to the system. You predict the load acting to cause the failure, and then you can predict failure or stability. What geometry do you need in a hopper to avoid this? These are some hoppers for cohesive clay that we've designed. No hammer rash on them, notice, because they've been designed using well-established models, I might add. Predicting the flow pattern inside hoppers. Again, this has come up once or twice. So the principle is empirical characterization, analytical model, predict stability or failure. Very successful. Thousands, hundreds of thousands of working designs. It also works for structural loadings on bins and other constraining walls and these kind of things. Other models for dense or slow flow that we've dallied with, numerical continuum models, modified CFD or FEM type models, for example. Broadly, for cohesive materials, we found that these have had limited success in trying to make quantitative predictions. And one of the main problems is that they don't deal well with this severe self-localization of shear and hence discontinuities. And that's a real problem there. The other problem is that our constitutive physics, which we understand reasonably well, is too complicated to put into these kind of models. They become too hard to solve. And the simpler constitutive models just are not sophisticated enough. For example, you can't easily predict core flow channel boundaries, which is a problem that we've been looking at for a number of years. So here's a couple of fundamental lessons about the truly dense state. You've got to consider powders as a state of matter in itself, separate from liquid, solid, or gas. And you've got to have a dedicated approach to their constitutive models. If you try and start with a system based around modelling liquids and you try and frig it to work, it just doesn't. And of course, this is because of the comparison between the properties of fluids or fluidized bulk solids and the properties of bulk solids in a dense condition. Let's look briefly at the intermediate state where momentum has an effect but not fully fluidized. Flow on top of a heap when you make it, avalanches, segregation, partially fluidized beds. Analytical models, not much success with these. Phenomenological test and scale up is where we're generally at, and that's broadly pretty successful. Continuum numerical models, some success if you calibrate them from the small scale, but what then if you have to calibrate it? What's the advantage over small scale testing and scale up? Segregation, intermediate flow we've got there. predicting segregation, again using these sort of combined models, and this is a result of a collaboration between our group and the group at Surrey. Segregation tester to get to actually measure segregation in a powder as it's handled, a numerical version of that, reverse engineer it to extract the transport coefficients, and then use those transport coefficients to predict what's going to happen in a full-scale silo. Works very well. Intermediate states, where momentum has an effect but not fully fluidized. DEM models, basically you'll never get enough particles because of the dispersion and the fact that the materials are polydisperse. If you've got a wide distribution of sizes, like in most real materials, for example, 100 to 1 size range between the 5th and 95th percentile, that means the mass ratio between the 5th and 95th percentile particles is 1,000,000 to 1. So if you're going to have 1,000 of the large particles, you need 1,000,000,000 of the small particles, then you've got to have the ones in the middle as well. It's just not on. But actually, as engineers, we don't care about that. We don't actually care about physical rigor. If the model predicts the behavior properly, if it's only based on 1,000 identical particles, but then it's calibrated somehow, that's okay. So a simpler model with a calibration, we're happy with. We haven't been able to actually get there yet. Likewise, combining DEM and CFD, DEM to on a small field so we can harvest constitutive behavior. No real success yet, but we might be able to get there one day. Looking at the highly agitated state where momentum transfer is dominant, such as fluidized beds, these kind of things, powder behaves like a viscous liquid, you would expect CFD should be able to deal with that extremely well. DEM, don't know about that. Very dispersed systems such as lean phase conveying. These are pictures taken in a sight glass in our lab, and you can see the kind of dispersity that you've got there. CFD and particle tracking, an Euler-Lagrange type approach, has worked very well for some problems, like predicting wear on the inside of bends. But we've never found it to be any good for predicting pressure drop or conveying rate. And the only way to do that is to do a test at a small industrial scale and scale up. So there's bend wear. Dense phase conveying systems, and this illustrates a problem with many real systems, they combine more than one state. In a dense phase system where you've got slug flow, you may have intermediate and dispersed phase. You may have dense conditions in slugs here, which then at bends rearrange in a fluid-like condition. Very difficult to try and tie all those models together. So there's a test rig that we use to test at the small industrial scale. What we've done is to try and refine the technique to make the characterization testing as cheap and as quick as reasonably possible. So mixed state systems, as I said, crossover is too expensive to model. Here's a few challenges, some of which might be doable. I've tried to keep out of these the things that I think are probably too hard. Anisotropy in powders. Take a block of powder, apply a stress all the way round. If sigma 1 equals sigma 2, what we call isostatic compaction, you will get the same strength in all directions. If you cut that on any plane, you get the same strength. But actually, that's rare in practice. That's not what generally happens. Most real processes, powder tends to be constrained. And what you get is something more like the uniaxial compaction, something like Oscar was showing you on Tuesday with his K-meter. And the problem with this is if you cut that in different angle or cut that at different angles, you get different strengths. And we've got no real way of even describing that, let alone being able to use it adequately. So powder anisotropy depends on how the powder's been compacted. The maths get hard. Would we be able to develop something in the way of a constitutive framework that would capture that we could use in CFD? Until we can, we're not going to be able to use CFD effectively for the really dense phase, in my view. This means, obviously, you cannot use a single pressure value to characterize the condition to which a powder's been compacted. You've got to account for pressures in different directions, and of course powder stores its history. This is another way in which powder stores its history. In homogeneity, when you've got cohesive powders, this is the result of an avalanche. Lots of little snow particles, they've settled, they've become compacted, then the bed has moved. And you've got here a lot of large agglomerates of small particles. But these agglomerates, they can be persistent, but they're not fully stable. They can break up, they can reform. And being able to deal with this is a real challenge. And particularly where you're trying to dose very small quantities of powder, this becomes a serious problem because the cohesive strength is not enough to break the agglomerates as you're trying to handle the powders. At the moment, we can't even describe it, let alone model it. So there's a challenge. Particles with extreme shapes, biomass, waste materials, all these kind of things. They sit on top of each other, they bend over, they nest, they interlock, you apply pressure and they get stronger. Traditional powder mechanics constitutive models just fail completely with these powders. We've got no way of dealing with these at the moment. We're actually starting on this journey this month with a new research project. And if anybody's interested in talking to us and seeing if we can learn anything from each other, we'd be interested to talk. A few more challenges very briefly. I mentioned effective extraction of good constitutive relationships from DEM models. This business of equipping continuum numerical models to deal with discontinuities, can it be done? I don't know. You probably know better than I do if that's a possibility or if it's completely out of the question. And this crossover between dense and fluidized beds. Finally, just to touch on validation of techniques, we need to know if we can use a model for design purposes as engineers. The test of usefulness is to set up a model and calibrate it so it models a small system accurately. That's our characterization. Then we use it without recalibrating. And will it predict accurately a larger, more complex system? And if we compare it against data from that large real system, that's the test of usefulness. And the measure of success, this comes back to what we were discussing the other day in Roger's session, is does it predict the aspects of behavior that we care about? It may not predict accurately some aspects of behavior, but maybe we don't care about those. If it does, we can use it for design on that aspect of behavior only. If not, it's back to the drawing board. It may mean changing the model. It may mean changing the small real system, in other words, the characterization test. Perhaps we didn't do the right small experiment. Maybe there's nothing wrong with the model. So I'm not going to offer any conclusions except to say whole variety of different techniques there, levels of success, you know, a personal view. Horses for courses, I think, is the lesson. Different types of conditions, different types of boundaries, these sort of things determine what types of model are successful for us. We have, because of the amount of work we do at Wolfson over the last 30 years we've been doing this, we've masses of real system data on industrial materials. If anybody wants to use it for model testing, they'd be very welcome. Thousands of case studies we've got. And maybe, because we continue to do these all the time, if anybody wants to harvest information in a particular way, perhaps we could help to generate it for their model improvement. And I'll finish at that point, and then you can all throw things at me. Thank you very much.
Thank you. Any comments or questions? Thank you.
So, we've heard a lot this week about the use of a particular simple one parameter, a method of modeling diverse dense granular flows using the inertial parameter. In your opinion, how far is that kind of approach from being able to provide useful modeling for industrial circumstances?
The limited use we've made of that type of approach has shown it to give useful signposts in terms of qualitative behaviour. but I've not seen any examples where it's been used successfully quantitatively. And I think perhaps this is the kind of test that we need to undertake, that perhaps what Roger was suggesting from an IFPRI point of view might be a valuable way of answering that question.
This is related to Thomas's question, but presumably in the industrial setting, nearly all the surfaces you're using are smooth.
Not necessarily.
But you wouldn't deliberately make your surfaces rough.
Very often you finish up with vessels which are rusty inside, and not uncommonly you may find that the surface roughness of the rust is bigger than the particles. Also, quite commonly you get materials bonding on the inside of surfaces as well, which is a major problem. So sometimes they are rough. Sometimes we make hoppers out of corrugated walls. There's an interesting challenge.
You emphasize cohesive particles. Is that because of wetness, or because the particles are small enough that there's van der Waals adhesion?
In many cases it's because they're fine particles, but also in other cases there may be, as you say, moisture, there may be oil, there may be electrostatics as well, but often, as far as we know, it's van der Waals.
Roger?
Yeah, I don't know that I'm so pessimistic as you are. I think where the need is well demonstrated, then the driving force to produce a solution exists. And I take fluidized beds as an example. I mean, going all the way from very simple engineering correlations now to full numerical predictions, and used as a design tool for carrying out chemical reactions. And this is done pretty successfully. So there's a whole, that's a specific class of operations, but it's one that is done because the financial benefit of doing that successfully and the cost of getting it wrong are just so enormous.
Well, I bow to your greater knowledge about fluidized beds than mine. I'm obviously trying to present what I know from my limited knowledge, but of course I don't know everything about everything. It's my sort of personal experience that I've come up against. But I think it's right what you say, that if something is very expensive, then it's worthwhile spending a lot more time modelling it, and that may be the justification.
And the other interesting aspect of that is from my experience within the IFPRI organisation is that go back 10 years, pharmaceutical companies knew nothing about powders. They knew a lot about chemistry, but they knew nothing about powder handling or powder mixing or blending or unmixing. But now they need to know that, and they're rapidly trying to get up to speed.
My experience is that in the past 10 years they've started to wake up to this.
Yeah.
Because manufacturing efficiency has become more important. Because there's less new drugs coming through the pipeline, they're more interested in holding on to their existing ones when they go off patent. So manufacturing efficiency has had a new focus. And pharmaceutical companies that we've worked with over the last 10 years have tried to develop and embed this kind of technology. But what we found is, with the current economic climate and the current downturn, many of them have actually run their engineers out of town. And so they've gone back 10 years virtually overnight.
Well, let's thank Mike again.